Imagine a place where the very fabric of reality is stretched and probed, where particles dance at speeds approaching the impossible, and where the secrets of the universe's birth and ultimate destiny are whispered in the language of subatomic collisions. Sounds like science fiction, right? But what if I told you this place exists, and it's pushing the boundaries of science so far that we're now seriously asking, are we alone in the cosmos, or do parallel universes shimmer just beyond our grasp? At the heart of this mind-bending quest lies CERN, the European Organization for Nuclear Research, a colossal scientific playground nestled near Geneva, straddling the border between Switzerland and France. Since the mid-1950s, this global hub of intellect has been the epicenter of high-energy physics, a field dedicated to unraveling the fundamental building blocks of matter and the forces that govern their interactions. Think of it as a giant cosmic puzzle, and the brilliant minds at CERN are tirelessly piecing together its intricate components. Their most famous tool, the Large Hadron Collider, or LHC. This isn't your average piece of lab equipment. It's the most powerful particle accelerator ever constructed, a 27-kilometer ring buried deep underground. Inside this colossal tunnel, protons, the very nuclei of hydrogen atoms, are accelerated to velocities just shy of the speed of light. Imagine two beams of these tiny particles hurtling in opposite directions, gaining unimaginable energy before being forced into head-on collisions within massive, sophisticated detectors. These aren't your everyday fender benders. When these high-speed protons smash together, their immense kinetic energy transforms into a shower of exotic subatomic particles, fleeting echoes of the universe's infancy, mere fractions of a second after the Big Bang. By meticulously studying the birth, life, and decay of these ephemeral particles, scientists at CERN are essentially rewinding the cosmic clock, peering into the fundamental processes that shaped everything we know. The primary mission: to test and expand the standard model of particle physics. Think of the standard model as our current best blueprint of the universe at its most fundamental level. It elegantly describes the elementary particles, quarks, leptons, bosons, and the electromagnetic, weak, and strong forces that orchestrate their interactions. It's a triumph of human intellect, explaining a vast array of experimental observations with incredible precision. However, like any good detective story, there are still unanswered questions, gaping holes in the narrative. The standard model, for all its successes, doesn't account for the enigmatic presence of dark matter and dark energy, which together make up the vast majority of the universe's mass and energy content. It also doesn't fully incorporate gravity, the force that governs the cosmos on the largest scales. These are the mysteries that keep the scientists at CERN awake at night, fueling their relentless pursuit of deeper understanding. That's where the advanced experiments at CERN come in. Situated along the LHC's ring are colossal detectors with names like Atlas, CMS, ALICE, and LHCb, each designed to scrutinize the particle collisions from a unique perspective. Imagine having 4 giant, incredibly sensitive cameras surrounding each collision point, each capturing different aspects of the resulting particle shower. Atlas and CMS, the 2 general-purpose detectors, are hunting for new, heavy particles, the kind that might shed light on dark matter or the Higgs boson's elusive companions. ALICE focuses on the quark-gluon plasma, a state of matter believed to have existed in the universe's earliest moments, while LHCb investigates the subtle differences between matter and antimatter. The sheer volume of data generated by these collisions is staggering. Billions of events occur every second, an overwhelming torrent of information that needs to be captured, filtered, and analyzed. This is where cutting-edge technology, particularly quantum computing, is beginning to play an increasingly vital role. Now, you might associate quantum computers with complex financial modeling or breaking impenetrable encryption codes, and you wouldn't be wrong. But for CERN, quantum computing represents a potential revolution in how they tackle their most challenging data analysis problems. Classical computers, the ones we use every day, struggle with certain types of tasks, especially those involving searching for extremely rare events within massive datasets. Quantum algorithms, leveraging the bizarre and counterintuitive principles of quantum mechanics, could potentially handle these kinds of searches and pattern recognition with unprecedented speed and efficiency. Think of it like searching for a single specific grain of sand on an entire beach. A classical computer would have to examine each grain individually. A quantum computer, however, could potentially look at all the grains simultaneously, drastically reducing the search time. This capability could be a game changer in sifting through the LHC's petabytes of data, allowing scientists to identify faint signals that might otherwise be buried beneath a mountain of background noise. Another crucial intersection lies in the realm of simulation. Understanding the intricate dance of fundamental forces at the incredibly high energies achieved in the LHC requires complex theoretical calculations, particularly in the realm of quantum chromodynamics, QCD, the theory that describes the strong force binding quarks together inside protons and neutrons. These calculations become exponentially more difficult as the complexity of the system increases. Quantum computers, by their very nature, operate using quantum states. This inherent quantum nature makes them potentially ideal for simulating certain subatomic processes far more efficiently than even the most powerful classical supercomputers. Imagine being able to accurately model the behavior of quarks and gluons during a high-energy collision using a quantum computer, gaining insights that are currently beyond our computational reach. There's also a more speculative, yet deeply intriguing, connection. Some theoretical frameworks that propose the existence of parallel universes also suggest the possibility of extraspatial dimensions beyond the three we perceive. While CERN isn't trying to punch holes into other realities with a quantum computer, these advanced machines could potentially help model how particles might behave if such extra dimensions were real. They could allow physicists to explore the theoretical consequences of these ideas, potentially revealing unique signatures that might then be sought in the LHC's collision data. Now, it's important to temper the excitement. Quantum computing technology is still in its nascent stages. The fundamental building blocks of quantum computers, called qubits, are incredibly fragile and susceptible to errors. CERN can't simply plug a problem into a quantum computer and expect instant answers. Instead, research teams are meticulously exploring which specific tasks within their vast research program are best suited to this emerging technology. Early experiments in using quantum machine learning for analyzing particle physics data have shown promise, but we're still a considerable distance from a quantum leap in real-time data analysis. Nevertheless, this burgeoning synergy highlights a crucial aspect of CERN's mission. It's not just about building bigger and more powerful accelerators. It's about embracing every cutting-edge tool available to gain deeper insights into the fundamental workings of the universe. If quantum computing can help confirm or deny the existence of parallel universes, that would be a monumental discovery. But even on a more practical level, the enhanced data analysis capabilities it promises could be the key to unlocking new physics hidden within the LHC's vast datasets. The CERN Quantum Technology Initiative, CERN-QTI, is a testament to this forward-thinking approach. This dedicated program actively explores the potential of quantum computing, quantum sensing, and quantum communication for the future of high-energy physics. One key focus is on developing quantum algorithms for event classification in LHC collisions. With billions of collision events occurring every second, it's impossible to store and analyze everything in detail. Machine learning algorithms already play a crucial role in filtering out the less interesting events. Quantum algorithms hold the potential to significantly enhance this efficiency, potentially identifying subtle signals that classical methods might miss. Researchers at CERN are also collaborating with companies that are developing quantum hardware. These partnerships provide invaluable opportunities for physicists to test their algorithms on real, albeit early-stage, quantum processors. Even with current limitations in the number and stability of qubits, these early explorations are crucial for identifying the bottlenecks and potential breakthroughs in applying quantum computing to high-energy physics. For instance, certain quantum optimization methods might significantly speed up the calibration of the massive detectors or refine the parameters used in complex simulations. Quantum sensing is another exciting avenue of research within CERN QTI. Imagine developing sensors based on the principles of quantum mechanics that could detect incredibly minute shifts in gravitational or electromagnetic fields, the kind of subtle disturbances that might occur if new physics processes, perhaps even hinting at extra dimensions, were taking place near the detectors. These projects are largely conceptual or in the prototype phase, but CERN's investment in them underscores its commitment to pushing the boundaries of measurement and detection. Ultimately, CERN's entire mission is about venturing into the unknown, both in the physical realm with its powerful accelerators and in the computational realm with its exploration of quantum technologies. From tangible gains in data analysis to the tantalizing prospect of uncovering fundamental truths about reality, the potential benefits are immense. If quantum computing lives up to even a fraction of its promise, CERN could witness a dramatic acceleration in the pace of discovery. Faster data crunching could allow for near real-time analysis of collisions, significantly reducing the years it currently takes to confidently identify and understand new phenomena. Beyond efficiency, quantum simulations could become a powerful tool for testing theoretical ideas before they are fully explored in real collisions. Imagine a quantum simulator providing a glimpse into how particles might behave in scenarios involving extra dimensions, based on a specific mathematical model. This could help researchers prioritize experiments and guide the design of future detectors, saving valuable time and resources. On the more speculative side, if our theoretical understanding of parallel universes advances to the point of generating testable predictions, quantum computing could potentially be used to model the incredibly complex boundary conditions of these hypothetical realms. While highly speculative, advanced quantum algorithms might be able to handle the intricate systems representing multidimensional environments or even holographic representations of spacetime. If such simulations could reveal unique signatures that might manifest in real collisions, it would bring us one step closer to bridging the gap between theoretical possibility and experimental evidence. Of course, these wilder possibilities remain firmly in the realm of theoretical excitement. The immediate focus is on leveraging quantum computing for more practical applications in data analysis and simulation. However, the history of science is filled with unexpected connections and breakthroughs. The development of quantum mechanics itself, initially a seemingly abstract field, led to transformative technologies like transistors and lasers. Who knows what new frontiers might emerge if we gain a deeper understanding of extra dimensions or alternate realities. With every step forward into these uncharted territories, however, comes the inherent risk of misinterpreting powerful new data. This is why the rigorous processes of peer review and independent verification are absolutely crucial in scientific research. Every claimed discovery must withstand intense scrutiny to ensure its validity. The idea of parallel universes, often relegated to the realm of science fiction, actually finds some intriguing, albeit highly theoretical, roots in modern physics. String theory, for example, postulates that our universe might have not just the 3 spatial dimensions we experience, but perhaps 10 or 11. Some versions of these theories suggest that these extra dimensions are curled up or compactified at incredibly small scales, rendering them invisible to our everyday senses. However, physicists have proposed that the extreme energies achieved in LHC collisions could potentially provide fleeting glimpses of these hidden dimensions, perhaps through the appearance of unexpected new particles or the apparent loss of energy into a dimension we cannot directly observe. Then there's the mind-bending many worlds interpretation of quantum mechanics. This radical idea suggests that every time a quantum event occurs, a particle making a choice between multiple possible states. For instance, the universe actually splits into multiple parallel branches, each corresponding to one of the possible outcomes. It's a truly staggering concept, implying an infinite number of universes constantly branching off from one another. While it offers a potential resolution to some of the paradoxes of quantum mechanics, it remains a highly debated interpretation with no direct experimental evidence to support it. None of these ideas, extra dimensions, or the many worlds interpretation, are conclusively proven. They are theoretical frameworks that attempt to address some of the fundamental mysteries of the universe. However, some of these frameworks do make predictions about phenomena that might be observable at high energies, and this is where CERN's research becomes relevant. When scientists at CERN analyze the data from LHC collisions, they are constantly on the lookout for subtle anomalies, deviations from the predictions of the standard model. If they were to consistently find patterns of unexpected particle behavior or energy imbalances that couldn't be explained by our current understanding, it could potentially be a hint of something beyond the standard model. Perhaps a new particle, an unknown force, or even an interaction with a hidden dimension. Historically, there have been instances where the LHC data has shown tantalizing anomalies, causing a ripple of excitement throughout the physics community. One notable example was a slight excess of events observed around a specific energy level in 2015. This bump in the data sparked a flurry of theoretical papers proposing new particles that could explain the observation, and inevitably, whispers of connections to parallel universes began to circulate online. However, as more data was collected, the statistical significance of the bump diminished, and it ultimately turned out to be a statistical fluctuation, a random blip in the vast amount of data. This is a natural part of the scientific process. Initial hints often fade away under more rigorous scrutiny. Still, the pursuit continues. The speculation arises that if quantum computing can be harnessed to analyze these complex collisions with greater sensitivity, or to generate more accurate and sophisticated simulations of theoretical models involving extra dimensions, we might be better equipped to detect the faint footprints of hidden realities. It's crucial to understand that a parallel universe wouldn't suddenly materialize within the LHC detectors. The signatures would likely be far more subtle, perhaps a slight deficit in the expected energy balance of a collision, as some energy might leak into an extra dimension, or the unexpected appearance of certain rare types of particles predicted by theories involving extended spacetime. The popular imagination, fueled by science fiction, sometimes conjures up dramatic scenarios of CERN opening portals to other universes. However, the reality is far more nuanced. Scientists at CERN frame their research in terms of seeking evidence for the theoretical predictions arising from models that include extra dimensions. If such dimensions exist and are accessible at the energy scales probed by the LHC, we might find indirect evidence in the collision data. It's fascinating how seemingly mundane data anomalies can ignite such widespread speculation about parallel worlds. There have been instances where unexpected readings or glitches in CERN's equipment have been seized upon by online communities as potential evidence of unintended interactions with other realities. Consider the rumors surrounding missing energy events or unusual bursts of energy detected by the LHC. While the scientific collaborations meticulously analyze these signals to determine if they represent genuine physical phenomena or are simply artifacts of the complex detectors, some members of the public interpret them as potential signs of energy leaking into or out of another dimension. To date, no stable, consistent pattern of such events has been confirmed that would definitively point to extra dimensions. Then there are the more bizarre and often highly publicized incidents that get attributed to CERN's powerful experiments supposedly messing with timelines or altering reality. The so-called Mandela effect, a phenomenon where large groups of people share false memories about past events, is sometimes linked to CERN's activities. Proponents of these theories suggest that high-energy collisions might somehow be causing shifts between parallel realities, leaving us with conflicting memories of how things used to be. For the vast majority of scientists, these claims lack any credible scientific basis. Memory is fallible, and group influence can easily explain shared false recollections. However, the very existence of such rumors underscores the public's fascination with CERN and the potential implications of its groundbreaking research. It's easy to see how real scientific facts, such as CERN finding unexplained anomalies in its data or CERN utilizing cutting-edge quantum computers, can be twisted and amplified into sensational stories about rewriting reality. Officially, CERN maintains a clear and cautious stance, emphasizing that their primary goal is to investigate the fundamental laws of nature at the smallest scales. Any truly significant anomaly would require extensive testing and a vast amount of additional data to be confirmed as a genuine discovery. Away from the grand, headline-grabbing ideas of extra dimensions and parallel universes, the daily reality at CERN is one of meticulous problem-solving. Thousands of scientists and engineers dedicate countless hours to ensuring the intricate detectors function flawlessly, carefully calibrating their responses, and meticulously logging the data from each experiment run. The data pipeline at CERN is a marvel of modern engineering. Collisions occur at such an incredible rate that specialized electronics must identify potentially interesting events on the fly, discarding billions of less significant ones every single second. Once data is flagged as potentially containing new physics, it is routed to a global network of storage systems. CERN relies on the worldwide LHC computing grid, a distributed network that harnesses the power of supercomputers, university computing clusters, and even commercial cloud services across the globe. It is within these immense computing resources that the painstaking process of data analysis takes place. Researchers from around the world sift through the collision data, searching for patterns or subtle anomalies that might match the theoretical predictions of new particles or rare particle decays. If quantum computing technology matures to the point of being truly reliable and scalable, it could be seamlessly integrated into this data analysis pipeline, potentially working in tandem with classical computers. Imagine a hybrid approach where data is initially processed by classical systems to identify promising events, which are then passed on to a quantum chip to search for subtle correlations that classical algorithms might overlook. The results from the quantum processor could then be fed back into the classical systems for further, more detailed analysis. While this vision is still some years away, it represents a potential future direction for CERN's data handling capabilities. Behind the scenes, the collaborative nature of research at CERN is truly remarkable. Thousands of individuals from diverse physics laboratories, universities, and countries form large international collaborations, each group focusing on a specific aspect of the data or a particular theoretical interpretation. This global and collective effort is essential for making progress in such a complex and demanding field. If a genuine, groundbreaking discovery, perhaps even evidence of parallel universes, were to be found, it would require widespread confirmation and consensus within this international scientific community. The everyday management of terabytes and petabytes of collision data might not sound as glamorous as hunting for hidden dimensions, but it forms the very foundation of scientific progress at CERN. Without the dedicated work of countless individuals in ensuring the integrity and accessibility of this data, the grand theoretical ideas about the universe's fundamental nature would remain just abstract concepts. One might reasonably ask, even if the search for parallel universes ultimately proves fruitless, why does the kind of fundamental research conducted at CERN matter for our everyday lives? The answer lies in the long history of unexpected technological spin-offs from basic scientific inquiry. CERN itself is credited with the invention of the World Wide Web. Tim Berners-Lee, working at CERN in the late 1980s, developed the web to facilitate the sharing of research data among scientists across the globe. This single invention has profoundly transformed nearly every aspect of modern society. Beyond the internet, advancements in particle accelerator technology have found crucial applications in medical imaging techniques like PET scans and in cancer therapy, where precisely directed radiation beams, originally developed for high-energy physics experiments, are used to target and destroy tumors. The ongoing development of quantum computing, in which CERN is actively involved, holds the potential to revolutionize fields ranging from cryptography and logistics to the design of new materials and pharmaceuticals. CERN's unique scientific demands and its collaborations with quantum hardware developers push the boundaries of this technology, potentially leading to breakthroughs that could have far-reaching impacts on various industries. For example, if scientists at CERN develop more robust methods for quantum error correction to improve the reliability of quantum computations for analyzing LHC data, those same methods could potentially be adapted to enhance the security of financial transactions or protect sensitive healthcare information. Another significant benefit of CERN's research is its vital role in education. Each year, thousands of students and young researchers from around the world flock to CERN to participate in cutting-edge experiments and learn advanced skills in computing, engineering, and physics. Many of these individuals go on to work in diverse sectors, taking their valuable knowledge and expertise with them, contributing to innovation and economic growth. This continuous influx and outflow of talent fosters a global culture of scientific and technological advancement. Finally, there's the intangible yet profoundly important benefit of discovery itself. Throughout history, human societies have progressed and adapted when we have dared to push the boundaries of knowledge. Even if the current quest for parallel universes doesn't yield direct evidence of other realities, the very act of exploring these fundamental questions inspires new generations to pursue careers in science and technology. The inherent human curiosity about the nature of space, time, and matter can energize entire fields of research, leading to unforeseen breakthroughs and a deeper understanding of our place in the cosmos. In this sense, the pursuit of seemingly abstract concepts like parallel universes or the intricacies of quantum mechanics contributes to a shared human story of exploration, a story that, while often theoretical, has tangible real-world impacts in the form of knowledge sharing, technological spin-offs, and international collaboration. Looking ahead, CERN is far from reaching the end of its scientific journey. The high-luminosity LHC, HLLHC, upgrade is a major project aimed at significantly increasing the number of particle collisions, allowing scientists to collect even more data and probe extremely rare physical processes with greater precision. This increase in data will place even greater demands on computing infrastructure, and it is in this context that quantum computing could begin to demonstrate its true potential, handling and simulating the massive influx of new collision events in innovative and efficient ways. Beyond the HLLHC, there are ambitious proposals for an even larger and more powerful collider, sometimes referred to as the Future Circular Collider, FCC. This proposed machine would dwarf the LHC in both size and energy reach, potentially unlocking new realms of particle physics and shedding light on even deeper mysteries of the universe. While the immense cost of such a project raises valid questions and debates, proponents argue that if we are truly committed to unraveling the fundamental secrets of matter, energy, and perhaps even hidden dimensions, we must continue to push the boundaries of experimental capabilities. In parallel with these ambitious accelerator projects, CERN's quantum computing collaborations are steadily advancing. Research teams are actively testing quantum algorithms on currently available quantum computers, acknowledging the limitations in the number and stability of qubits. As quantum hardware continues to improve, these early studies could pave the way for the integration of quantum computing into the mainstream data analysis pipeline at CERN. If successful, this could significantly accelerate the process of evaluating the plausibility of various new physics theories, including those that propose the existence of extra dimensions. The hypothesis of parallel universes remains a captivating, but as yet unproven area of speculation. If extra dimensions do indeed exist and are within the energy reach of our experiments, the coming decade could potentially bring the evidence needed to either confirm or refute their existence. Conversely, if no evidence emerges, it would provide valuable information, prompting us to refine our theoretical models and explore alternative avenues of investigation, such as more precise cosmological observations or new theoretical frameworks in quantum gravity. The overarching takeaway is that CERN is a dynamic and ever-evolving scientific endeavor, constantly pushing the frontiers of human knowledge. The pursuit of understanding the universe at its most fundamental level is a complex and challenging endeavor, and where this chase will ultimately lead is anyone's guess. But as long as the LHC continues to accelerate particles to near light speed, and as research into the bizarre and promising realm of quantum mechanics advances, the captivating stories of parallel universes, quantum gates, and potential doorways to other realities will continue to spark our imaginations and drive the relentless quest for deeper understanding. Thank you for joining me on this journey into the heart of scientific exploration. If you found this exploration of CERN, quantum computing, and the tantalizing possibility of parallel universes as fascinating as I do, please consider subscribing to the channel for more in-depth dives into the wonders of science and technology. And while you're here, be sure to check out the other captivating videos on your screen. Wishing you all the best of health and continued curiosity.